right, let me start my session. All right, hello everyone. Thank you for coming to my session today at the Iceberg Summit 2025. My name is Tasuku Okuda from Japan. Today, I'm excited to share with you some real-world use case study and challenges we've faced while adapting and utilizing Apache Iceberg within our data platform at LY Corporation. Okay, right. And in this session, I focus on real-world use cases and its background motivation. So I think my session is good for Iceberg beginner who is considering to adapt Apache Iceberg into their own data platform system, but not decided yet. Okay. All right, let me briefly introduce myself. I currently work as a senior engineering manager in the data pipeline engineering division at LY Corporation. My career started since 2013. I joined Line Corporation as a new graduate, which is former company of current LY Corporation and provide a mobile chat application called Line globally, especially East Asian countries. Through several data-related project experiences, like multiple internal hardware cluster merging, I built my career on data platform engineer and technical project leader. In 2023, as a senior engineering manager of data engineering department, I've been deeply involved in the evolution of our data infrastructure. Apache Iceberg is one of them. Okay, here is today's agenda. First, I will give a brief introduction to LY Corporation. I guess LY Corporation might not familiar to everyone here in the United States, so I will take some minutes to explain our business. And second, I will provide an overview of our data platform architecture. And third, and this will be my main part of today's session, I will dive into 4 specific use cases of Apache Iceberg in our companies. I also show the background motivation and technical detail. And fourth, I will show current challenges we encountered during our Apache Iceberg journey. And finally, I will summarize the key benefits that Apache Iceberg has brought to LY Corporation. All right, let's start with a quick overview of LY Corporation business. LY Corporation is one of Japan's largest tech companies formed in October 2023 through the reorganization of group companies, including 2 biggest IT and web companies in Japan, Line Corporation and Yahoo Japan Corporation. Our mission is to create an amazing life platform that brings wow to our users. Essentially, we aim to a part of our users' daily lives from morning to night, providing service that surprising, inspire, and improve their lives. We've continuously expanded our service and user bases, deepening our impact. Our goal is always to leverage technology to create new value for our users. Our business portfolio is quite diverse. For example, we have a messaging application, Line, which is one of the most famous messaging applications in East Asian countries. We also have e-commerce service like Yahoo Auction and Yahoo Shopping, which have been around for a long time in Japan. And we have news, media, and search engine service, a lot of service. We also built strategic partnership with our group companies, especially PayPay and its ecosystem, one of the biggest fintech services in Japan. As our partner company, sorry, not partner, as our parent company, we have SoftBank and we form a strong partnership together. This is one range of services and partnerships generate a massive amount of varied data, which is crucial for driving our business forward. Okay, to give you a sense of our company business scale, let me show several key metrics at LY Corporation. We reached over 320 million users across our group services. And in fiscal years 2023, our revenue reached over 1.8 trillion Japanese yen, about over 20.8 billion US dollars based on the currency rate at that time. And our services are available in approximately 230 countries and regions. We have a large team with over 28,000 employees and around the world. These employees work in over 100 different companies within our group. These numbers show the significant volume of user interaction and data generation across our platform. Also, because we provide various services in multiple countries and our group companies has different business styles, we need to handle complicated data governance and management strategy. Okay, next, let's look at the data platform overview technical session that supports all these services and enable data-driven business. All right, this diagram shows a high-level overview of our data platform architecture. Maybe it is not surprising things. A lot of data engineers here know this well. All right. Here is Kafka and Flink and Spark and Torino, and strategy is Apache Hadoop. So it is very common software, open source software. We built our data platform is based on open source software. And on the left of the diagram, we have a various service system due to a lot of businesses in our company. Service developer implemented data processing logic inside their own system. They often send the data into our full managed ingestion pipeline, typically using Apache Kafka and Apache Flink for real-time processing. This data runs into our data platform storage HDFS. We have a high meta server as a central data catalog to manage schema and partition. And there is an authentication layer for access control to any dataset based on both policies, company-wide data usage regulation, and each service original privacy policies. On the top of storage, we have a couple engines like Torino and Apache Spark here. And also data engineers through and platform system like Apache Airflow for workflow engine and Kubernetes for common computing environment. And the right side of this diagram, these tools are used by various stakeholders, data engineer team for building pipeline, and machine learning engineers for building model, and data scientists for service growth analytics, and also business analytics for customer metrics reporting. We also have data owner distributor involved in data management via our data catalog. This architecture served us well, but as our scale grows and world is updating, we've reached a point where our system needs to evolve. All right, here is the key metrics of our clusters. HDFS total capacity is over 1.1 exabytes. And now more than 100,000 tables we are managing, including Hive format and Iceberg format. And data ingestion pipeline throughput from service system is around 1.5 trillion records per day. This scale highlights the needs for more efficient, scalable, and reliable data management solution. All right, now main session. Let's dive into the specific use cases where Iceberg has provided significant value into LY data platform. All right, use case one, partial data deletion. This becomes increasingly important due to several factors. Ever-changing data-related law. Due to personal information regulation like GDPR, we have more demand about data granular control for user privacy protection. And next one is complex environment. We have many products and service, but each one might have a little different privacy policy. So it is very important to handle requests to delete data flexibility. And the third one is accidental recovery. Sometimes incorrect data might be ingested into our data platform. In this case, we need to correct our data set quickly to avoid side effects like daily batch or daily summarized batch. So what we needed is a way to delete specific, potentially small amount of data, some row or few columns, with a reasonable operational cost. So traditional Hive table often required rewriting entire partition over table, which is too expensive and slow, even for small target deletion. So Iceberg offered a solution through a feature like margin read with position deleted. Assured transaction ensuring safe concurrent operation and impress stable evolution for schema changes like a drop-in column. Well, let's visualize the challenge with traditional method. Please imagine this table with Hive format. If we need to delete row 2 over drop column C using standard Hive table format, we typically have to read all the data file in the affected partitions, filter out deleted row or column inside the query engine, and then rewrite the entire data file. It is easy to imagine that it will be painful, take a lot of time, sometimes several hours, but sometimes dozens of days. Even worse, during this operation, data will be unavailable. If we try to read that table or partition during this deletion operation, it might be return wrong result because several files might be still rewriting, but others not. So with Hive table format, any query engine cannot control each file level status. For large table or partition, this is very costly operation in terms of computing resource and time and decision making. Well, so now let's compare this to Iceberg. When we execute delete from DB table where row ID 2, Iceberg doesn't immediately rewrite the main data file. Instead, using the merge on read strategy in version 2 format, it writes a separate delete file that makes the specific positions of the row to be deleted. Similarly, dropping a column like outer table DB table drop column C, it is just a metadata operation. Iceberg updates only the table metadata, which is significantly smaller operation cost than actual data file rewriting. So query engine reads the metadata, data file, and delete file, all of them. They show the correct table data without requiring immediately costly rewrite. This greatly improved our operational efficiency for handling partial deletion. The actual merging of data and data file, or physical removal or drop column data, can happen later during Iceberg table maintenance operation called compaction. I will discuss about compaction and table maintenance later. And the next use case is reducing data latency. There are two motivations. One motivation is our previous implementation of stream ingestion pipeline often had a delay of over an hour before data became queryable. This is because of hourly conversion job to ORC. This day is one of the blockers of near real-time analytics. And also, we face scalability issue with downstream system of full-text search engine. We use OpenSearch for near real-time data analytics and monitoring like system testing and QA and customer support. For those use cases, real-timeness and stability are both important. So, we wanted to make streaming data available for querying within a few minutes, not hours. To achieve this, we use Iceberg async transaction and asynchronous compaction strategy. This diagram illustrates our previous pipeline. Service-side data is ingested from Kafka through Flink. Flink writes this incoming data into HDFS as sequential file, containing binary data, which is serialized as a predefined protocol buffer message. A separate process insert override job was needed to convert this data into an analytic-friendly format like an ORC columnar format. Along with ensuring data was fully flushed, this conversion step introduced significant latency before the data was available to the query engine, as I said, over an hour. So with Iceberg, the pipeline is much simpler and faster. Flink write directly to the Iceberg table in an optimized format like Parquet. Thanks to Iceberg transactional commits, Flink can commit small batches frequently, in our cases, every minute. This makes the data immediately visible to query engine like Torino or Spark almost as soon as it's committed, which means only minutes level latency. When we commit data to the table often, it can create many small files. A different process called table optimizer fixes the problem later without interrupting the main work. The process runs compaction job asynchronously in the background, merging many small files into fewer larger ones. Optimize the file without blocking any concurrent writer and readers. This allows us to achieve low latency, minute level latency, while maintaining query performance and efficient storage utilization. Okay, next use case is a FlexSim schema update. Motivation is here. Business needs change very often and quickly. Because of this, we often need to change how our data is organized and managed. For example, we might add columns, rename them, and change their order, or even remove them. Also, it costs time and effort at the beginning to define perfect schema. This can make the initial development and decision-making take longer. In historical reason, we have been using a position-based ORC format for a long time. Operational like dropping column or reordering them could be problematic because the data interpretation lies on the column's position rather than its name. We considered to change them to name-based, but gave up because rewriting all dataset was obviously high cost. So to make our triangular process faster, we need a way to evolve schemas easy without breaking downstream consumers or requiring complex data migration. The key is Apache Iceberg robust schema evolution capabilities. All right, let's illustrate the problem with a concrete example using position mapping. Imagine a service developer initially define a log message with ID, optype, and message field. Data is written based on the structure in the right table. These column positions are 1, 2, 3. Here 1, 2, 3. And later, the developer needs to add a log time field between ID and optype. Here is green one. And delete an exit field message. Here, red one. The updated schema become ID, log time, and optype. The writer process previously write a second column optype and third column a message. But from the point of schema update, it tries to write new data into the same table with a new schema, expecting a second column is log time and third is optime. In this scenario, if the query engine tries to read the old data before schema updating with new schema, second and third column data will return incorrect value. Second column tries to return optime value for log time definition, and third column return message string for optime expectation. This causes data interpretation issues. So Iceberg solved this elegantly. Each column in Iceberg table is assigned a unique field ID, independent of its position in the scheme definition. The initial schema might have a field ID, ID1, and op type, ID2, and message ID3. Data file written with schema ID 0 are associated with the field in the metadata and manifest related file. The updated schema add log time ID4 and remove message ID3, very similar as the previous example. New data file schema ID1 are now being written with the new schema, mapping the data to ID 142. When a query run, Iceberg uses the table current schema but read all data file. It uses a unique field ID stored in the Iceberg metadata and associated with each data file to correctly map the data. So it doesn't matter how the data was structured when it was written or where the where the column located in the field. Right. Iceberg can still follow proper data position and understand it correctly. This allows seamless addition, deletion, lemming, and reordering of columns without breaking compatibility before and after schema changes. Our final use case focuses on improving the scalability and stability of our metadata layer, specifically addressing high metastore bottlenecks. We have tables with tens of thousands of partitions, and in my vast experience, I saw over 10 million partitions in the single table. It was very nightmare, and I know such huge number of partition creation is very bad practice in the data platform world. But in our early use cases, data creator who actively work on our data platform is not only data engineer, but also various type of employee like data analytics or sales guys or general developer who may not have enough knowledge of data engineering. Also, building partition for such table by high metastore can be extremely slow and resource intensive, putting a heavy load on the high metastore service and its backend database. Furthermore, poorly written query could trigger full partition scanning. This could cause a big problem by putting too much load on the high metastore because our high metastore is a single point of failure. So we wanted to reduce the load of the high metastore, especially for partition listing operation. So Iceberg manages it on metadata like partition information and actual data file location or table table stats, which is stored directly on the storage system like HDFS. So it doesn't rely heavily on the metastore for the partition detail. Okay, here's the traditional Hive table format approach. When a query engine needs to build a query execution plan, it asks the Hive metastore for a list of all partitions matching the query's filter. For a table with many partitions and query with a per partition filtering condition, the Hive metastore retrieves potentially huge list from its backend database, in our use case, MySQL. And this involves significant database load and potentially large amount of data transferred back to the query engine, often causing high heap usage in JVM of Hive metastore. In worst case, Hive metastore faces out of memory issue and stops the world, which leads the entire cluster hang out. So Iceberg change its dynamic significantly. When a query engine builds an execution plan for an Iceberg table, it first fetches only the basic table metadata from Hive metastore. Essentially, the location of the current Iceberg metadata file. Then, the query engine reads the Iceberg metadata file, like a metadata file or a manifest list or a manifest files, directly from the file system HDFS. This file contains detailed information about the data files, partition value, and column statistics per file. HDFS is very reliable solution for huge amount of data accesses and throughput and concurrency controlling, better than high metastore. So we can finally avoid full cluster hangout thanks to Iceberg metadata fetching strategy. Very importantly, partition pruning happening within the query engine itself, not high metastore, using the information efficiently in the located Iceberg metadata files. Especially partition stats stored in manifest files. The engine can quickly determine which data file are relevant to the query without needing to ask the high metastore. This dramatically reduces the load of the high metastore, making it more stable and scalable on entire cluster and often speed up query planning for highly partitioned tables. Alright, this slide is an updated architecture diagram showing the point we upgrade when adopting Apache Iceberg. First point in the ingestion pipeline. Our managed ingestion pipeline has started to support near real-time data landing, as I said, based on Iceberg table formatted into HDFS. The developer who implemented producer logic doesn't care any difference between previous Hive-based ingestion pipeline and new Iceberg ingestion pipeline, thanks to Flink streaming processing logic. Service-side developer just produce their own data into Kafka one by one with predefined protocol buffer protocol. And the second one is catalog system. Our catalog system supports both table format, existing Hive format, and new Iceberg ones. This provides a good feature to see current table and partition status and those metadata in same web UI, regardless of its table format. And the third one is computer engine and BI tools. Also, we have introduced Apache Iceberg support into Torino and Spark. And to minimize data analysis running costs, our internal BI tool automatically determines the proper option to consider when using Iceberg and adjust runtime parameter accordingly. Those Iceberg support in each platform component wasn't easy, take a lot of development and test costs. But despite such development costs, there was a strong motivation and significant benefit to implementing Apache Iceberg for our use case in LY Corporation. Okay, here's the key metrics related to Iceberg. We now have over 8.2 petabytes of data stored in Iceberg tables. And this constitutes over 9,000 Iceberg tables and a significant portion of our daily ingestion, around 1.2 trillion records per day, flow into this Iceberg table with near real time. This number demonstrates that Iceberg is not just an experiment for us. It is a core of our data platform. We have started to expand Apache Iceberg into production scale system by handling a massive workload. Okay, next section. While Iceberg brought many benefits to us, but the adoption journey wasn't without its challenge. Let's discuss a couple of key ones. First challenge is table format migration. I joined several sessions today, but a lot of people mentioned about their challenge to migrate existing Hive environment into Iceberg. Our data platform has a similar situation. Over 10 years history started with Hive. So there are a lot of file format tables in our data platform. Also, we have promoted data democracy. By this democracy strategy, there are a lot of stakeholders in our data platform. Even in a single table, There is multiple stakeholders, a data owner and a few data stewards and multiple data readers. So even for small changes, we need clear approval from the data stakeholders and must be very careful to operate. I know Apache Iceberg documentation officially provides several approaches to migrate a Hive format table into Iceberg format. We consider impress migration, adding Iceberg method into existing Hive table without writing data itself. We are in the process of planning this migration, ensuring the step and the safety and efficiency, and confirming rollback procedure in case of any problem. In another aspect, we need to take care how to change existing DistCP operation. Yeah, we heavily use DistCP for copying among storage, especially backing up our data set from HDFS into AWS S3. Our DCP, our DCP strategy is partitioned directory based. So we need to build alternative way to copy a part of Iceberg table to another storage based on split point. And the second challenge is table maintenance. As you may know, if we introduce Apache Iceberg format, we need to keep maintaining it. Without maintenance, we will face several critical problems like performance issue or small file problem. Each manipulation of Iceberg table we made several files into HDFS, which sometimes become large. In fact, some of such files are unnecessary in real-world business. Too many files and metadata brings lower usability, and if the number of files grows too many, we may face HDFS small file issue again. However, not all platform users can understand Iceberg internal and its maintenance importance and strategy very well. Our platform user mission is to improve LY business based on data, not maintain platform system. So they don't care about Iceberg maintenance. In our approach, we introduced a Spark-based job called Iceberg Table Optimizer. A lot of data related to vendors provide similar solution. As far as I know, Cloudera already supported automated protocol or system, but for now, we built our own ones. This diagram shows the architecture of our internal Iceberg Table Optimizer service, designed to automate the maintenance task of Apache Iceberg. There are several components, and I will explain one by one. One is the coordinator. This is running as a Spring Boot application. This is central component periodically check Iceberg table to determine if there are any Iceberg table which required optimization based on configuration and stats information. It looks at metrics like the number of small files, presence of delete files, or number of snapshots, etc. And the second one is task queue. This is Redis queue. When the coordinator identify a table needing maintenance, like compaction or expire snapshot, it submits the required task to the query, to the queue. And the third one is Worker Runner. This is running as a Kubernetes cron job. It's checked periodically the task queue and determines the optimal number of Spark workers needed based on the queued task and table stats. It compares this with the current running workers. If more workers are needed, the runner submits Spark job as workers to our Yarn cluster. And the final component is workers. This is the Spark job, and the Spark job pick up a task from the queue. It then executes the necessary Iceberg maintenance procedure using the Iceberg Spark library, like write data files for compaction or expire snapshot directly against the Iceberg table. This entire automated system helps ensure our Iceberg table are consistently maintained for optical performance and storage efficiency, and reducing the manual troublesome operation costs on individual chip and standardizing the maintenance process across all data platform users. All right, to wrap this thing up, let's summarize the key impact of adopting Apache Iceberg at LY Corporation. As we've seen through the use cases today, Apache Iceberg has brought significant benefit to our data platform. One is a partial data deletion, and second one is reduced data latency. Third one is flexible schema update, and fourth is scalable and stable metastore. So this technical advantage also lead to bigger improvement in what we do with data. One is the business agility. Faster data available and flexible schema allow our development teams and analysts to respond more quickly to changing business needs, and it's faster on that product. And system quality, reducing latency and improved metastore stability and efficient maintenance contribute to a more robust and reliable data platform. And the third one is governance flexibility. Easier data deletion and schema management improve our easier data deletion and schema management improve our ability to adapt to changing regularly requirement and internal data governance policy. So finally, by enhancing governance flexibility, system quality, and business agility, Apache Iceberg is helping us accelerate data-driven decision-making and growth across LY Corporation. It has become a fundamental technology enabling us to handle massive scale while improving efficiency, flexibility, and speed. All right, before I go to the thanks slide, I'd like to thank Claudia very much for their big help with engaging to build our data platform, introducing Apache Iceberg adoption. Also, I'm thankful for the chance to speak in the cutting-edge data technology community Apache Iceberg Summit. We truly believe our strong partnership helped us achieve this important result to share that we can share with everyone here at the Iceberg Summit. All right. Thank you all very much for your time and attendance today. If you have any questions later, feel free to reach out by email or LinkedIn. Thank you. And question time? Is there any question for my session? A little bit nervous because I'm Japanese, so.
Go ahead, please. I was just curious if you considered other catalogs other than Hive, so any REST catalog implementations, if you evaluated those?
Like a Polaris or something?
Yeah, I'm a Polaris committer. Yeah, or Polaris.
Actually, we are considering now, but as I said, all right, let's go back to the scale. Yeah, there's a lot of table metadata inside our data platform, over 100,000 tables. So currently, our decision is very hard to migrate all of them. So if we introduce alternative solution for metastore, we try to separate our data platform, especially metadata, into a small portion of based on the business requirement. So if we can decide to divide our data platform, it is a chance. But currently, there's no plan. All right. Is this answer? All right. Okay. Thank you.
Thank you so much for all the insights shared. I do have a good question regarding the compactions that you build like a system that manages compactions for you. I'm just curious, like, so you have like more than 9,000 tables, and do you have the same rules that you apply for every table, or you have some abstraction, or like how exactly you compact each table, or do you have a need to like apply different parameters to every table, or you just use the default compaction for all those?
Right. Thank you for the question. Currently, yes, As I said, our table, our old table is managed in high metastore. So yes, we provide a guideline to use this table optimizer based on the configuration inside high metastore, which means table properties. So the table owner try to put several configuration inside Hive table properties, and automatically the worker automatically checks the properties and decides the strategy how to compact or how to compact when start the compaction or something. Is this answer? Hmm. Okay. And also, yes, one more thing. Currently, not all Iceberg table is compacted automatically. Yes, currently we provide this system for platform users like opt-in style. So if user wanted to manage automatically, we ask to put Iceberg table optimizer equal true inside the table property. And then automatically this coordinator try to check high metastore, all Iceberg table properties inside high metastore, and then automatically compaction and purge several open file or etc. automatically. But some user doesn't want to check, doesn't want to maintain, doesn't want to operate several maintenance tasks automatically, like yes, high-skill user like machine learning people. So in that case, they try to avoid to run this system automatically without no setting about inside the table properties. Yes, right? Thank you. Is there any question? Maybe time is over. Okay. All right. Thank you. Thank you for listening.